Hi, everybody. Welcome to the UW Robotics Colloquium. This is the first colloquium of the fall quarter. And I think several of you are new here in the program. So I thought that's actually a really good opportunity to give you an overview or a sampler of the kind of research we're doing in the NVIDIA Robotics Lab, which is kind of up the street. As many of you know, I spent most of my time actually over the last 2 years at NVIDIA, where I kind of put together a robotics group and a robotics lab for NVIDIA. And as of last week, I'm now back at 50-50. So I'm spending half my time here at UW and the other half at NVIDIA. And I think there's great hope that this will actually work out well for everybody, also for my students here at UW. So again, what I wanted to do is kind of give you an overview of some of the work going on in the lab, and I will not be talking about that, but it's the researchers from the lab. This is part 1 today, so we'll have, after me, there's going to be 3 short talks, and in 2 weeks we'll have kind of the rest of the researchers giving you an overview of what they are doing. And the main idea of this is also that you can see kind of the research that we're doing and hopefully see connections to your own research, and then we can have collaborations on these, right? Because the work that's going on in the NVIDIA lab is open source, open publishable, so you don't need to be afraid that if you collaborate with us, it's all kind of hidden somewhere and you can't talk about that or use it, for example, for your PhD research. Just a little bit of background on the lab. So how this started, a bit more than 2 years ago, I met with Jensen Huang, the CEO of NVIDIA, and we talked about robotics. And my feeling was, and still is, that this is kind of, when you talk about the kind of robots that we see that are actually being deployed in real application settings, these kind of systems where you have robots doing delivery tasks in hospitals or in hotels, and more also in kind of fulfillment centers, warehouses, and now moving into these spaces where the robots kind of navigate on sidewalks and do delivery tasks, and at some point we might even have self-driving cars. But if you think about it from a high-level perspective, it's really just kind of about getting from A to B without crashing into something, right? So the full focus is on do not make any contact with your environment, okay? And the kind of research that, of course, we here at the UW are really focusing on, and which is the next generation of robots, are these robots that actually physically interact with their environment and seek contact with their environment. The industrial setting of that, you can see here, is kind of these robots in these big car manufacturing assembly lines where they are pre-programmed to do super highly specified tasks that are very repetitive. So they just have to do thousands and thousands of times of exactly the same motion. And if this is all well designed, of course, it works really well. But one thing you can clearly realize here, there's, for example, no people nearby these robots because they are way too dangerous, right? So the kind of robots that we want to look at the NVIDIA lab, but also a lot of the work going on here, of course, at UW, is really the robots that interact with people, that can be interacting with them in a natural way. So hopefully you can just tell your robot what you want it to do. You can teach your robot what it should be doing. And these robots should be also interacting with you in close proximity. So the research challenges are very different from the pure navigation kind of tasks, right? Because here the robot, if it wants to help you, if it wants to pick up objects, or for example, here is from a colleague, Charlie Kemp at Georgia Tech, did some investigation on how the robot could help, for example, a person that's quadriplegic, shaving, then suddenly obvious you need to seek physical contact. How can you do that safely, and how can you do that in a meaningful way? So this is the kind of robot systems that we would like to really enable, so that it's not just working in small research lab environments, but out in the wild. And we all know we're still far away from that. But again, this was the motivation for NVIDIA to start this research lab, which is about 20 minutes walk from here. If you're slow, it might take 25 minutes, but I think I can certainly do it in 20 minutes. And so we are, some of you might know, there's Trader Joe's on Roosevelt Street. We're just kind of the parking garage. We're in this new Commotion building there on the top floor. It's really cool facilities. I'm sure many of you have already seen it. Different kinds of robots, but again, focus is a lot on manipulation, robots with hands, robots more with grippers, also on mobile basis, as you can see here. The research team is right now, we have about 15 researchers, and 2 of them are part-time faculty that spend time with us, which is Byron Boots from here. So he's spending 20% with us and spent the last 2 summers actually full-time in the lab doing research, also with the interns. So in the summer, for example, we had 20 interns doing, I think, pretty cool projects. So we had, I think, 15 ICRA submissions came out of that. And the other one is Animesh Garg, who is now a faculty in Toronto, but he's also collaborating with us. And what I find is really exciting that this is a very interdisciplinary research team. So it's not just people who know about robot control or robot kind of perception, but they're also coming from core computer vision, simulation, more mechanical engineering, for example, background. And of course, a core area nowadays is machine learning, deep learning, reinforcement learning. We're also collaborating very closely with the Isaac Sim team, which is, as many of you know, NVIDIA has very cool simulation engines, and we're working with them so that we can build tools that are really useful for the robotics community. The main application domain we want to look at is initially drive the research through this kitchen application, where the idea is that if you have a robot operating and doing tasks in a kitchen, you can almost make it as hard as you want, and you can also kind of initially make it kind of as easy as you want, right? And the notion is that really tasks in a kitchen, they can represent any kind of task that you would see in manufacturing settings or in settings where robots help people with disabilities, or robots help elderly people lead an independent life. So what we did is we went down to IKEA and bought an IKEA kitchen. So you can see this here on the upper left. And that's what we're using for a lot of the kind of integrated research we are doing. That is also an important aspect, that we don't want to work just on small isolated projects, but more also larger scale integrated systems. And the software that we've been developing for this research, it's also major portions of it will be shared, most of it open source, but we're also looking into that we can actually give access here to the robotics teams earlier on so that we can use it for our own research here at UW. Here's just one example. It's kind of the robot putting these 2 items in the cabinet. And how we do this, we have 2 depth cameras that observe the kitchen. With these depth cameras, we are tracking the model of the kitchen. We have a 3D articulated model of this kitchen. It's doing 60 pose estimation of these objects. It's also tracking where the robot is, because the robot can move around. And then we do, of course, the trajectory planning and real-time control of the manipulator to achieve these kind of goals. Okay. And again, of course, these objects can move around, so it's not like pre-programmed that they have to be at an exact location, right? They're all detected with the depth cameras, and later Yu is actually going to give you one example project that we're working on how to do that. Once you have that, you can then integrate that with, for example, higher level task and motion planning. This is actually something that just came out of an internship project. Kalen Garrett from MIT, he spent the summer with us as an intern, and he's an expert in task and motion planning, but their problem has been that it's not easy to actually get this to execute in the real world rather than in just more simulated setting. So here's just an example where the robot now has to find the spam can, which is one of these YCB objects, and it doesn't know in which drawer it is. So the first thing it realizes is, oh, I gotta get the sugar out of the drawer so that I can close the drawer, or I can look inside the drawer. And then it can open the other one. And now it found the spam, it localized it. And that was just the task, to figure out where the spam is, right? In this task, for example, it has to find the spam and then put it in the other drawer, right? So in this case, it opened that one, saw it's not in the lower drawer, and then it goes up there, looks inside, hooray, found the spam. Now you got to actually pick it up, put it on the counter, close the drawer and open the next one, things like that. So you can see that actually the planning behind that is not trivial, right? It's really longer term tasks, and we are now at a level in the setting where we have objects models that we can really implement them and run them on the real robot. Caveat, this is not 100% sure working yet, always, because sometimes the object pose estimation is a bit off, and then the gripper doesn't really manage to pick up the objects. But I think this is kind of giving you an example that we can now really look at more complex tasks rather than just picking up an individual objects. One thing that I'm super excited about is also that, of course, NVIDIA has a lot of resources on the simulation side. Here's one example where we also worked with the content creation team to build a simulated version of the kitchen that also looks actually pretty realistic. So what you see here is our robot executing, putting whatever, the sugar in the drawer or something like that. One is simulated and the other one is real world.
Which one is which?
Well, that's, come on, vote. Hands up for left is real. Hands up for right is real. Oh, awesome. So, which one is it? The left, you can see, some people see it, it actually depends on what you look for, right? But some people see, oh, there are these electric outlets in the wall, so that looks more realistic or something like that. But it's not trivial, right? So we can get now to kind of the simulation level that you can imagine that you can also use these settings to train your perception system, to test your robot control system, and also, of course, reinforcement learning, you can train in these settings. Again, as a caveat, this is only available for that single kitchen right now, and it's not easy to build such a model. It's actually, there's a lot of effort involved in that, and I think one of the future research questions is really how can we automatically generate content for these things. Yeah. Great.
So where's the camera? Your 3D camera, right?
Oh yeah, the camera. In this case, it's actually not on the robot. We have it kind of hanging from the ceiling. But the next step is clearly we're going to put it on the mobile robot as well. So with that one quick, so we're also looking at a hand, and you'll see a bit more examples for what we're doing with that. But just kind of, we had out of internships last summer, actually, we had 3 ICRA papers this year with various aspects of how to deal with touch sensing, how to learn predictive models from touch sensors, and then use them for grasping objects and moving them around. You can see here on the right is also one where it kind of visualizes kind of a learned model, because the touch sensor input or the sensor measurements you're getting, it doesn't really tell you the force and direction of the force. It just gives you very noisy actually pattern on the electrodes. So again, today and in 2 weeks, we'll give you a sampler of the different projects going on so that you also get to meet the research team. And today we'll kick it off with Clemens, and then you, and then Ankur and Karl are going to talk about some hand stuff. And first person up is going to be Clemens. If some of you have seen the Star Wars, which was totally awesome, right? So he said this was actually, building the model of the kitchen was harder than building a model of the Battle Star, the Death Star, or whatever in Star Wars, because the difference is if you build these for games or for videos or so, or movies, then if you say, oh, that doesn't really fit that well, let me just move the wall a bit further back or something like that, right? And it just has to look good. But if you want to use or build a really good simulation of the kitchen, then the sizes have to be exactly right, right? If, for example, the drawer doesn't fit in, then things might just blow up, as we know, right, with the physics-based simulation. So it took quite a while. And I think it's actually an interesting question. How can we very quickly generate these by just walking in a kitchen?
I mean, if we could, we would put the gaming companies out of business, right? Because that's what they do all day.
But they move ahead, yes, exactly. All right, so
So my name is Eppner. I'm going to talk about a project that we did about object grasping, and in particular about grasp sampling. So we're looking basically at the geometry of objects and how that relates to generating grasp data. So our motivation is basically that we want to kind of devise these learning-based algorithms, and I guess Arsalan, my colleague, will talk about this particular example in the part 2 next time. But the idea if we want to devise these kind of supervised algorithms, the question is how do we generate the data, the supervision data for these grasps? And if we don't want to only limit ourselves to these typical top-down planar grasping scenarios, then it's important to basically capture all the grasp distribution of an object, especially if we're also looking in these confined spaces in the kitchen where we don't want to have any grasp that works, but very particular grasp that might also serve a particular function. And if you look into other grasping papers where learning algorithms are presented for grasping, you look how the data is represented. This is usually written in a small paragraph as a side note. Here you see an example. To do so, if you first choose a random hand orientation, then choose a random hand movement direction, and then we slide the hand across the object along the sample direction while keeping the orientation fixed. So this is basically the way grasping data is here generated. Another example, another heuristic here, rays are cast from all sides of the object's bounding boxes. The intersection points are used as approach points and the surface normals as approach vectors, and similar things that you will find in other papers. And the question that we ask is can we evaluate this in more detail and maybe see some patterns here? And what is actually the best way to generate data using these heuristics? I can give you the references I didn't want. Yeah. So first of all, we try to classify this in kind of a taxonomy that is basically structured around how these grasp sampling mechanisms are guided by which kind of type of information. And the first big distinction is whether they actually use whether the grasp outcome is successful or not. And the second distinction is what type of geometry information they use of the object. And so here we have in particular these first two categories that don't use any information at all. They completely sample the space uniformly. This was the first example that we saw previously. And what I also listed here are some publications of work that has actually published data sets. So there's more work that actually use these techniques, but they don't have publicly available data sets. And the other big categories that I will focus on in this evaluation are basically these types of heuristics. They somehow use geometry, the geometry of the object to sample grasp based on the normals. And I will talk about this in a little bit of detail. And these two big categories are basically looking at the contact configurations of the grasp or looking at somehow the approach direction. And the last one, which I exclude in this talk, is basically to actually also use the grasp results so you can be a bit more fancy about your sampling scheme. So let's look at these two big categories. So what is shown here is an object and a parallel jaw gripper. So all this evaluation is based on parallel jaw grippers. That's the kind of limitation. But of course, this can be somehow scaled. And the assumption in these anthropodal-based schemes that you see a lot, for example, in DexNet or something like that, is that you first sample a point on the surface, then you get this kind of cone along the surface normal that is parametrized. And this defines sort of this line where the gripper will actually grasp the object. And then there's this distance, which usually they use the length of the fingers, and this defines sort of your grasp frame. So the definition of a grasp is here just a pose in SE3. And we ignore the internal degrees of freedom of the gripper. In the approach-based parameterization that we choose here is basically, again, you have a point on the surface and you have sort of this cone around the surface normal, but then you choose a vector that actually points towards the origin of the grasp frame. And there you have another cone, which basically you can also vary how the orientation is not orthogonal to that surface normal.
A quick question.
Yeah.
Is the pre-shape always fixed to be completely open?
Excuse me?
Is the pre-shape of the hand always fixed
Yes.
to be completely open?
There's always, it's always maximum grasp aperture. So we don't look at the internal degrees of freedom of the hand. Yeah. So because the idea is now what we want to compare in these schemes is not simply how good they are at finding good grasp, but actually how good they are at covering the entire space of possible grasp for an object. And to measure that, we kind of do something which is pretty brute force. We take a set of objects and then we discretize the space of grasp, which is now this SE3 thing. And we discretize it in terms of translation and orientation uniformly, so with 5 millimeters and 7.5 degrees. And then we sample, we choose all those grasps on this grid, and we evaluate them. There's one strong assumption, which is that if there's nothing between the fingers, we assume that it's a failed grasp, so we don't even simulate it. And the other strong assumption is that if it's in collision with the object, it's a failed grasp. For the rest of those grasps, which are for these 21 objects from the YCB dataset, the around 1 billion grasp, we use a simulator, Flex, to actually simulate the grasping motion, which means closing the fingers and then having a test for whether the object stays within the fingers by shaking it. And basically, by doing this, we have this, yeah?
Can you talk about how can you play that video? How does the simulation actually work? Is it running any pre-contact, pre-grasp interaction? What's it doing there?
No, it's basically just closing the fingers and then lifting it.
At what point do you turn on physics?
As soon as you start closing the fingers. So the assumption is...
Do things rattle around in the hand when they're getting...
Yes.
Is it on the table? Like, what is it on?
There's no gravity in that simulation.
Oh, no. There's no gravity?
No, because then you need to define... Yeah,
This is like grasping in space.
Right.
And you're not selecting the grasping of the phone, you're just assuming it's like this and then you move the object around, right? In this case.
Yeah, but that's the same. That's
okay.
That's
Why
equivalent.
Does it fall then? Is it falling because of like?
That's just inertia.
Inertia.
Because
I guess it's like rocket boosters that like, wow, this is cool. Why is this relevant?
Why?
Grasping in like the real world.
Why is this relevant for what? For the real world?
Yeah, where there's gravity.
It's just a simple, I mean, you can see it both ways, but gravity gives you implies a particular task because now you have a direction of gravity, right?
But the lack of gravity doesn't imply generalization. Gravity always exists. Just because gravity gives you a particular task doesn't mean that gravity doesn't exist in general.
So we did also some ablations with applying random disturbances to the grasps instead of having the shaking motion. And
but I mean, I think the pre-grasp interaction between the fingers and the object is what causes grasps to succeed or fail. And that's largely driven by physics, which includes gravity and friction and things like that.
I mean, friction, all that stuff is of course in there, right?
But it's floating in space.
yeah, there's.
We can
talk
take off
offline.
like that.
Yeah,
Okay.
I just want to, or yeah, please.
Sorry, what's the GPU here?
It's I'm not sure. That's not Titan XP. That's the V100 or what is it? Yeah. So as a result, you get those densities about the objects. And each little point is basically a successful grasp, and the coloring is based on how much the object moved during the post-grasp shaking or in the pre-grasp interaction. And you can use these densities now to actually compare these different samplings. Apart from that, we wanted to also show that this data is kind of not completely irrelevant for the real world. So here are some examples of grasps that we simulated that we tried in the real world to show that those grasps are actually also robust in the real world. And we also compared this to the real simulation. So let's come to the results here. So here what you see is basically the coverage. Coverage is defined as all the grasps and those densities that we saw what is covered by those different heuristics, those different grasp sampling schemes. So there are two things to note here. So on the x-axis, you see the number of samples drawn, and on the y-axis, you see coverage between 0 and 1. And you see these two families, the approach-based samplings, which are the red ones, and the antipodal-based one, which are the green ones. And the blue one is basically the uniform. You see that the blue one kind of converges to 1, as it should be. And the other thing to note is that actually these antipodal ones kind of have also a quite big bias in there. So they saturate around the way below 1.0. And I will quickly show what these examples are of structures that are being missed. The other interesting thing is it's kind of a bias similar to a bias variance trade-off. If you look into these first samples, if you look at the first 100,000 samples, you see that those with a larger bias, like the antipodal schemes, are much better at creating those diverse grasps. So if you have a low sampling budget, then this might be still the beneficial way to generate your grasp data.
So the goal here is to discover good grasps, right? Not to try every possible grasp.
Good, diverse, to capture. So coverage is basically all possible grasps, right? So,
but all possible grasps that work, or all possible?
No, all possible grasps that work is based on the simulation results.
But
of successful
do you test
grasps.
it to, I mean, typically grasps fail because they're not robust to pose perturbations. And that's not being tested here, right?
This is not being tested here. So we have a separate test where we define a robustness about the epsilon neighborhood of a single grasp. And then we also compare this to this subset. But the results, the tendencies don't change.
And how is it? How do you think this compares to? So, for example, like one way you can sample is uniformly on the sphere, but the other way you can sample is to bias it along the surface normal.
Right.
That produces a non-uniform distribution.
That's basically what's happening in these for these surface approach-based samplers. Yeah.
Okay. Okay. Anyway, go ahead.
So here are some examples of this antipodal scheme that are kind of missed, and you see basically that it's that you might argue that these are not really the best grasps that are missed. So, for example, on these sharp corners, like grasps that come from the side that are not aligned with any of those surfaces are those that are being missed. Or here also these high frequency features in these geometries are not captured. Or again here, where the approach doesn't really matter in the scissor case, but you don't get these normals from the model.
What is the meaning of each dot? How does each dot represent a grasp?
So you don't see, it's basically the gripper origin of the gripper frame.
So in the middle, somewhere in the middle of the gripper?
Yeah, it's the wrist basically of the gripper. Yes, so the summary is grasp sampling heuristics contain some bias. This antipodal-based scheme seems to still be the best choice. There are some things in the data that are not beneficial. One is also what Sid related to, that the grasp conversion, that it might be not realistic. Some assumptions like something in collision is not necessarily leads to failure. There are some aliasing effects due to the discretization of the space. And some open questions are still what is actually the best strategy, not only in terms of number of samples, but in terms of actual computational costs. And also given a particular learning algorithm, what is actually the best training data, because you might not only want to have all the positives grasped, but you want to have grasps that are kind of on this boundary between being successful and not successful. If you want to go and learn good models. Okay, thank you.
Maybe one more question before while you is setting up.
Really nice work. One of the challenges that I've faced with antipodal grasping is that it doesn't create a uniform distribution on the unit sphere. And because of that, when you're actually approaching, when you're pre-shaping to approach, the possible grasp might be in collision. So a very simple example is you have a coffee mug that is inclined like this, then all the normals are pointing into the table. And so if you're choosing purely antipodal grasp, then you're going to try to approach it from underneath the table. And that's never going to work. So there needs to be some combination of sort of uniform sampling on the unit sphere such that you have diversity of approach angles with stability. Right? Like a lot of them won't be stable, but that at least from your images, it seemed like there was strong bias on the unit sphere, which was caused by this antipodal sampling.
Yeah, maybe. Yeah, I think we should talk after offline. I'd like to.
So why would the antipodal, why would that?
Well, if you're always approaching along the surface normal, right, then one of the challenges that you face.
Oh, but for the antipodal, I think what they're approaching is the fingertip, not the wrist. So if the fingertip comes from there and then closes.
No, but you have to also choose how your
your wrist
is oriented.
Yeah,
right?
Okay, so I'm Xiang. After we have grasping from Clemens, but how can we localize objects so we can apply this grasp, right? So I'm going to talk about the software where the public future for 6 object pose tracking. For 60 object pose estimation, right? So we're on the problem. If we have a 3D model of objects, given an input image, can we estimate the 60 pose? That's basically the 3D translation and the 3D orientation of objects in 3D. And pose estimation is really used for object manipulation or semantic navigation, human robot interaction, and so on. So traditionally, how people solve this problem, right? We can basically classify them into feature-based matching or template matching. For feature matching, you basically have a 3D model you constructed with feature attached to a 3D model. And given input image, you have image features. Then you match this 2D feature and the 3D feature from which you can compute the 60 pose. Like Seed has done this moped method that's well known for manipulation in robotics. But template matching is you have a 3D model, you can render multiple views, and cause each view has a template. Then you can do a starting window on the image with a template, and that tells you where the object is, and also the template has an orientation. So you can estimate the translation orientation. But what's the challenge here, right? We want the model to have a super capability. Like we want to deal with texture objects, textureless objects, symmetric objects, unsymmetric objects, and all these objects to be in cluster, right? Also, can we achieve really high accuracy and robustness, right? The message should be very robust in lighting change, different background, or even have uncertainty of the environments, or should be fast, right? You don't want to wait a long time to get a pose. So this is deep learning play important though. It's basically because it learns better image features, also gets a strong model capacity. So in general, how this method works is you have an image, it feeds into a neural network, then you get a very good feature from a neural network. But then 2 ways to use the features. First way, you can still do object detection, get a bounding box, and from that, you can estimate the 3D rotation. The bounding box will tell you the 3D translation. Or you can do key point based. You can detect these key points, and then by matching the 2D key point and the 3D key points, you can estimate the 60 pose. So this is really similar to the traditional way, right? You can do template matching as you detect bounding box, or do the feature matching, you detect key point with deep neural networks. But our goal here is really, we want to handle symmetric objects, and we also want to do tracking, like in a video, we can consistently track the object pose, and also want to estimate the pose uncertainty. That's previous method I haven't tried with deep learning. Pose uncertainty basically meaning how accurate your pose estimation is. And this is really important when you want to do some decision making, right? If the pose is not good, I don't want to grasp. But the pose uncertainty is not that trivial. It really depends on context, shape, and prior. For example, let's take a look at this can, right? If you have a textureless can, the pose is really ambiguous because of shape symmetry.
from this view, it's either on the top or on the bottom. You don't have texture, so it can be all 360 degree around. But if you have texture, right, this breaks the symmetry. From this view, you know, okay, the poles are basically centered on that view. But also depends on the view, right? If you see the object from the top, you don't know it's top or bottom. So that's also introduced uncertainty. If you manually specify all these ways of handling symmetry, that's not feasible, right? So how can we deal with this symmetry? But last year, ECCB, Sandermeyer et al., they proposed this very clever idea. They train autoencoder. So the input image is objects with different background, different color, with different occlusions. And they train the autoencoder to reconstruct a very clean image without background, no occlusion. So then the embedding in this network, right, the middle column, basically encodes the appearance. If you think about two views, if they are symmetry, they will get very similar embedding. So you can check the symmetry by comparing the embeddings. So with this autoencoder, right, we have a 3D model, can render a large number of views, and each view you can compute the code from the autoencoder. That's reconstruct the code book. Given input image, you can still apply object detection to get objects, then extract a code by running this detected objects to the autoencoder, the encoder parts, then compare the code against the code book and get a similarity score. So you can pick the best one by matching the code and the code book. So if two views are symmetric, right, you get multiple picks in the matching. That's how you can handle symmetry. It doesn't matter which view of the symmetry pose you get, as long as you match one of them, it will be fine. But this method handles symmetric views, but they only estimate orientation. The translation is from some object detection, and also single view. There's no tracking and single estimates. There's also uncertainty in the pose estimation. So in this post RBPF, we propose to use based on particle filtering and do 60-pole tracking. So the Zau-Black-Weiss idea is basically in a particle, you don't sample all the states, but you just sample part of the states and solve the rest analytically. In this post estimation problem, we sample translation, but for the rotation part, we can estimate the rotation distribution based on the autoencoder. So the Zau-Black-Weiss basically means we just sample the translation, but solve the rotation with the autoencoder. Like here's one example, given an input video, post-RBPF is able to estimate the translation of the bow by doing this particle filtering, and also we get a full orientation distribution. That's this dot shows the distribution of this orientation. Because of symmetric bow, so you will see a 360 degrees around the bow. So in post-RBPF, how we represent particles? Particle consists of two parts. The first one is the 3D translation. The second one is the orientation distribution. From the 3D translation basically determines, the orientation distribution is we discretize these views, right? We can have a large number of views and use the autoencoder to construct a code book. That's how we get this orientation distribution. It's discretized. So the translation part in the particle determines where the object is in the image. So we can crop the image to have a region of interest. And we use autoencoder to compute the code for the image and match against the code book and get this rotation likelihood. That's a discretized orientation distribution for these many viewpoints. But in particle filtering, once you get a new image, how do you update your particle? The first step is from the previous frame, we have a set of particle. Now we can propagate this particle to the current image, and this particle determines the bounding box on the in the image. For all these particles, we can have the region of interest, and also by matching the code book against the code book, we have orientation distribution for these particles. Based on the propagated particles, we can feed this region into autoencoder again, compute the particle codes, and match against the code book to get orientation likelihood. So basically, that's the observation on the current image. We combine these two to compute the posterior. finally, we can normalize this posterior getter weights and resample the particles based on the weights. So here one example of the tracking of this mark. Now you don't see the handle of the mark, so that's why the particles somehow uniformly distributed. But once a handle appears, right, then this particle will just focus on the side because the handle will disambiguate the symmetry. So, we did some experiments on some benchmark. So this shows it's able to beat the previous state rods. I'll just quickly go to some recent work. Post-RPP is great, right? But how can we achieve the robustness we want? The general idea is we do self-supervised learning. Because post-RPP is generally trained on synthetic data. Once we apply to real world, there's some failure case. How do we fix this? If a robot can automatically learn by itself to fix these errors, that's really nice, and to achieve like a lifelong learning. So build this self-supervised 60-pose estimation system. The robot just with a camera on the hand, it just move around to collect images and estimate the pose with post-RPP for these objects. It's also able to pick up objects to rearrange the scene so you can capture new data in the real world. And it pushes the object to generate a new scene. But basically based on the post-RPP, we are able to really get accurate ground truth pose for these objects. So we can use this data to retrain our system and to improve it.
What's the latency?
Sorry?
What is the latency of your component of the system?
Latency, you mean speed?
Sure. Whatever you want to call it.
I think it's, for each estimation depends on how many particles. The tracking will be 5 frames per second. But
like end-to-end image to output, what is it? It's 5. You can do it at 5 frames a second.
But with 50 particles, one object is going to be 20 frames per second. Depends on how many objects. Because we want to track all the objects in the scene. If you have more objects and more particles, it's going to be slower.
Yeah, for like this scene, how was it? What was it like?
I would say 5 frames per second for these objects. But because we have camera in the hand, we can use forward kinematics to propagate the particles. That's help tracking this object pose.
How did you get the labels for like the ground truth for the real world?
Basically from the pose estimation. We have a pose evaluation. The pose applicator estimates the pose, and we check if the pose is good or not. And we only keep the data with the good pose. So that.
But then you're also using it to train the RBCS?
Right, because the uncertainty tell us how accurate the ground truth pose is. Once we decide to save the data, we'll make sure it's really accurate. Okay. Right. And it's not okay. Just to show, okay, this system is able to collect a lot of videos and a lot of data to train the system, and it's able to improve the grasping success rate from like 46% to 86 among 30 grasps. So I'll just skip this. It's just with this thing, it's estimate the pose first, and then use Clemens grasp and do the cleaning table task to pick up the object, put it in the bin.
So this is I'm getting a little confused here. So you're running a filter here, right? So it requires multiple views. Or just a single view? Are you using like I'm confused by the use of the particle filter because you use it in 2 ways, right? One as like sequential importance resampling using particles.
Right.
It doesn't necessarily need to have a motion model and an observation model. The other is the more traditional like thing that Dieter and co invented, which is that you have a motion model, you have an observation model, you run Bayes filter through the motion model and the observation model. So you're using it in the former sense of just using particles as a non-parametric representation for densities?
Yeah. It's a single image stream, like a video.
We need a video stream or not?
We need to process the image one by one, right? It's in time. But
so just to clarify, because maybe as a robotics guy, we do a full particle filter over time.
I see.
With motion model and everything.
I see. Okay, got it. And then the motion model is something that is given to you. So it could be on an arm or something.
Right, or it's just random Gaussian noise. Or
the random Gaussian noise would be like the condensation algorithm, right? It was invented like, I don't know, 30 years ago.
No.
But,
condensation is a particle filter, right?
Right, it's a particle filter with just random Gaussian noise. But here you have an actual motion model that comes from the robot arm.
Right, because the camera in the hand. But if you have camera outside, you don't have this information.
So the motion model needs to capture both the camera motion on the robot and the motion of the object, because the object itself can move too.
Correct. Yeah, that
So
was what I was going
both.
to ask. But it needs that's something that is an input to your system.
Yeah, exactly.
Somebody else's problem. Yeah. Okay. Got it.
Okay, I'll just.
So I'm assuming that these are RGB cameras rather than depth cameras?
It's RGBD, both.
Oh, because you were talking about lighting variations.
Lighting will affect the RGB image, but we also have depth image. That's important to achieve that higher accuracy.
Yeah, the depth image lighting effects won't.
Right. For lighting, it's standard.
Okay.
Also, just to clarify, I mean, this is like a meta algorithm, right? So it would work with any pose estimation algorithm, essentially. Like, it doesn't particularly need your algorithm for producing pose hypotheses or does it?
Provide pose hypothesis for.
Are you so like everything that you said, right? You're taking the particles, like pushing it through the coding to turn it into a fixed length vector,
Right.
and then combining it, running it through a particle filter. Like, I guess that could work with any provider of object pose. I mean, filters are in general very general
Right.
entities, right? But here you're proposing something that is specific for your previous algorithm.
It's basically this autoencoder to have a distribution of the orientation. It's not a single estimate. Like your particle is represented by translation and the distribution on
Yeah,
the.
so
On
what I'm saying is anything that emits a distribution or rotations can be plugged into your system, right? Not necessarily like your method for emitting distributions.
I think so. The particle filtering is
So
quite
that's
general.
actually a good feature.
Yeah,
right?
quite general.
Just confirming that.
Right.
Okay. Hi everyone. We're here to talk about a new system called DexPilot, which is a depth-based teleoperation system for robot hand-arm system. So first of all, what is the motivation here? So there are multiple reasons to do teleoperation. We've seen that with the DARPA Robotics Challenge has different levels of hybrid autonomy for search and rescue. Then NASA has been doing teleoperation for years for medical treatment in space because they can't have doctors in space. Then space EVA and many other things. And why do we care about multi-finger things? Because we can augment a kinematic capability of the current systems with multiple fingers, and we can solve a lot more things. So here is what Karl did, who's going to speak again, in NIST in 2018, where you have lots of amazing things being done with the multi-fingered hand. Then this OpenAI work that came out last year, and that recently we've been doing things at NVIDIA where we have touch sensors on the hand and allows us to do closed-loop cup following. And then we have multiple other reasons to do teleop is learning from demonstrations, assisted grasping, et cetera, et cetera. We've seen all sorts of amazing demos with RL lately, but we will find that most of them actually end up exploiting the bugs in the physics engine or cheating in some way or the other. So here is, in the first case, it learns to open the drawer by just pushing at the corner. Then the hexapod learns to walk upside down, not the kind of intended behavior you would like. And then in the Atari game, it learns to go around, knock across the wall, and starts collecting points without exploring the game, because they found that strategy that gives it really lots of points. And then we feel like Humanintheloop is going to be really helpful to guide the solutions that we would like. And we have multiple reasons, and there's lots of work in this direction in the past couple of years. And we've also seen that Humanintheloop in NLP lately, because that's also one of the examples where having human actually guiding the solutions helps produce better output. So the contemporary solutions that we've seen with teleop tend to be glove-based, and they tend to be pretty expensive and bulky, et cetera, et cetera. And there are other solutions in AR/VR that tend to focus on low degrees of freedom with limited field of view. And then the other spectrum is motion capture systems that tend to be super expensive as well. So what we want is a solution that does not have any drift, it's low cost, and it's glove-free and markerless, and it can work for dexterous multi-fingered solutions. Here are some of the examples that we are able to do. And this is the system architecture. We have all the 4 cameras housed on a table overlooking where the hand is moved. So ultimately, you want the system to work within this arena. So And then there's a real table and a robot there where we are able to do in close proximity line of sight teleop. So this is the architecture. They have 3 different modules which are stringed together in a daisy chain. And the first is the learning thread, which actually uses all the information from the point clouds of 4 cameras fused into one to give us the initialization of the hand pose. And then you can use your classical optimization-based methods to refine the solution, because CNN-based solutions tend to be roughly good, but not quite. And then you have another module, because we want to now teleoperate on a different hand, which is different to a human hand, so you need a kinematic retargeting optimization as well. And the third one is actually the control loop, which basically executes position-based impedance control in the real world. So the PointNet architecture is basically a 2-stage architecture, where the first stage actually segments the hand in the scene, because we need to first localize the hand. The second stage refines the solution. So here is an example of that, where we have actually hand moving on a table, which is really nice that we can then fit a plane on the table and get rid of the points on the table. We are left with the points actually on the human body. And then we can segment the hand using all the point cloud information, but it only gives us rough estimate, which we can refine with another stage. So now we have a very good estimate of the hand, which we can use with continuous optimization on top to refine, which Karl will explain now.
My name is Karl Van Wyck. I'll finish the presentation. So as Ankur mentioned, we now have initial predictions of what the pose of the hand is, and we also have estimates of what the joints are doing for the fingers themselves. And we just want to clean it up a little bit more. So we send that information into a piece of software called DART that uses it as a prior, and it further calculates cost, which matches how the points of the point cloud hit the geometric model of the human hand. And we found that overall the performance is just better to incorporate this stage as well. It smooths things out and makes the accuracy a little bit better. So out from DART, what we get is the pose of the hand, and we also get joint angles for the human hand model. So we need to go from that to the real robotic hand, which is actually much larger than our own, and the joints are in different places, and the axes are in different places, and it's very difficult to just operate in joint space to match one to the other. So we ended up using a task space cost function to kind of capture how to relay one to the other, which boiled down to a series of vectors that point between the fingers in and among them, and also the fingers to the palm, which captures where the fingers are with respect to the palm and where they are spatially distributed among one another, and as well as their orientation, which was very important for grasping. So it's a fairly straightforward. There's some subtleties in there. One other thing that we also do is, and this is optimizing this cost function across the joint angles. So we end up solving joint angles for the Allegro hand. So one other thing that we do here to compensate for inaccuracy in the hand tracking is when you do things like this, where you're actually literally pinching, there's a perceptual gap where you have like 1 or 2 centimeters between the fingers. And the more fingers you clump up, the worse it gets. So what we do is once there's a projection volume, once you come into this volume, all those fingers that are that close get projected together. And so you can actually be enabled to pick up something very thin or emit more forces on smaller objects. So what does this look like? This is a set of canonical shapes that translate from one to the other. As you can see, it captures a large variety of hand poses, fully open, half closed, intermediate curl states, things like that, as well as when you're actually trying to intentionally pinch on something, you can see that contact is being made between the fingertips themselves. So you stand a chance of actually grabbing on something that's quite small. To reflect back on the architecture that we zoomed by before, we now have joint angles for the Allegro hand. We have a hand pose that we want to control. We send all this information to our RMP motion generation framework, which calculates full body joint angles for the full system to solve given those inputs. And those targets are then sent to the low-level torque controllers that actually execute the motion of what we want. So here are some objects that we've been looking at. They span quite a bit in size, shape, rigid, flexible. We do pick and place. We do pouring. We do opening of drawers, twisting things opening, inserting, stacking, all kinds of things. So there's a lot of rich manipulation tasks that we were able to now unlock immediately, which is quite nice. So here's some set of videos I'm going to show. This is an extremely long multi-stage problem to solve, which would be a nightmare to solve otherwise, especially with a system this complex. But dropping the human in the loop, we can now actually get sensory motor solutions that we can ingest and train later on. But it means that we need to manipulate this container, unclip the sides, take out this box. And now this box is folded upon itself, and you actually have to pry open the lid and actually be able to open up the box container to get at what's inside the box itself.
Can you comment on I mean, this is remarkable how humans can do these amazing tasks under teleoperation and continue to be fascinated by that. Is there a reason why you had to go slightly slowly? Because like,
we wanted to.
You were very capable.
So this came, yeah, sure. This came from an Icar video where we had only so many minutes to put things in, and we wanted the videos to actually end at the same time. We've played around, or I've played around in the past where you'd have one finish if you keep the same multiplication factor.
I guess you could. There's nothing non-intuitive about the interface or anything that prevented. Because in my experience, when you have such a nice teleop interface, you can.
Right.
Not only can you perform dexterous tasks, but you can perform them at speeds that are pretty remarkable.
Yeah. Right. So I mean, some of the tasks take longer than others, and we do have some lag in here that we're dealing with as well.
Quick, another clarification. Like, is there a reason in the retargeting that you did? Is there a reason why you chose to ignore the pinky? Sort of like ignoring something
we
else?
don't have one. In the
No. Like you could have chosen to ignore this finger, right? Like I'm just asking what your intuition was. Like, yes, I know that there's 4 on one side and 3 on the other.
Well, your ring is closer to your middle, so it might be weird to try to target off your pinky instead of. Yeah, I mean, we didn't try that. We can certainly try that, but I think
just curious
my intuition was that keeping the fingers in order was probably something to shoot for first. Yeah. So you saw some of the other videos there as well.
I think with respect to speed, was it mostly? I think the end is still maybe the tracking, that we can do these motions, right? And the Allegro hand can do the same speed of motion, but tracking that robustly and accurately, is that the main limitation, or?
Well, tracking certainly can be improved.
Yeah.
I think we are also very conservative with the control.
Yep.
We can make it run very fast, but then it might sometimes overshoot and might not do exactly what you want it to do.
I see.
So you have to be careful. The good thing is that humans are really good metal learners. You can exploit them to do whatever you want.
Yeah, and that was I think we're doing something similar with chopsticks too. But like I think one of the interesting things is that no matter what interface you give humans, the retargeting, they learn in like 2 or 3 tries to remap. I think that's a valuable thing.
So, can you say something about the latency of the tracking and also the accuracy? Like, have you compared it against the mock-up system to see how accurate it is?
So accuracy as such, I think we haven't done that. The reason being that as long as you can solve these tasks, we are fine. And the latency can be 1 to 2 seconds, but also.
Wait, what?
No. The latency is sub-second.
Between the, like, how fast is your state estimate?
30 frames.
Oh, the hand tracking.
30 frames.
30 frames a second.
So, and there's no pipeline. So it's like about 30 milliseconds delay.
Right. End to end, it's a little under a second delay from moving to seeing robot motion.
Yeah, so
Some of that has to do. But if you get rid of the robot, from moving to seeing an animation.
Right.
That's
much faster. Yes, that's.
And still 30 milliseconds or a second or what?
No. That's at 30 hertz.
Yeah. So the hand tracking is at 30 hertz.
Yeah.
He means, is there a pipeline, like,
So
I mean,
the
the
whole
camera
thing,
buffers and then the thing goes there, that is processed, so there's a pipeline of things being processed, so he's asking the length of the pipeline. Like, you know what's the latency? Not in,
Overall pipeline?
Yeah, the latency.
So the overall latency is 1 to 2 seconds?
No, from motion to seeing the motion is being detected on the screen, like the
Just for hand tracking.
Just for
yeah,
the track.
that's 30 seconds. It's
30
really-
milliseconds.
30 hertz, sorry.
No, what is the latency? Not the
Yeah.
frame rate. That's
I
what
don't
he was
think we
asking.
measured the lag itself,
Yeah.
but it's quite, you don't notice it. It's pretty instantaneous. Okay. So these are results. So the way we measured this is you perform 5. Oh, there was one more question.
So the actions that you perform are not optimal.
Where?
I'm down here.
Oh, okay.
The actions you perform, that you get the robot to perform, are not optimal. So if you're training some policy on top of that as sort of supervision, is there any way of fixing it?
Sure, there may be some optimality there, but it's certainly better than what we have currently, which is no solution. So yeah, I mean, we can think about ways to like improve on that.
And I mean,
Yeah.
one point of doing this also, we can start using that then to train policies, right? And then that question comes up: can we even be better than the human demonstrations?
There is some work on given suboptimal demonstrations, what to actually get from it that makes you even better. Yeah, there's already work being done on that. Yeah. So I think
In the interest of time, maybe let him just finish quickly, and then people can start leaving too while we have more discussions. I would suggest.
So we measured success across 5 consecutive trials, so you don't just pick your best results per task. So you can see the spread of success rates and mean time to completion. You can see how the difficulty of tasks escalate that as well. Ultimately, if you're interested in doing demonstrations to teach a robot, if you happen to fail on one trial, well, you can just do it again. So in that sense, this is still very practical. And that's it. Yep. So it's just a little highlight reel. Any questions?
Yeah, I just had a small question, which is, did you look at whether adding like fiducial stickers to the hand could improve performance, like IR stickers or something?
We didn't. Suspect it probably would. We were trying to get away from putting markers onto stuff, which is known to be a tried and true solution to this. But then you need a system that can support that, and those, depending on which one you get, can run tens of thousands of dollars. So we decided to not go that route. Yeah.
So I want to push back against this marker thing. You can glue like a reflective 3D tape on the back of the fingernails. Use pretty cheap cameras these days to track those. Like Ultrax sells you cameras for like $100 that run at 120 hertz and give you like pixel accuracy. And so these are basically the perfect features. Like some silly neural network can never compete with that. And then you can basically nail the tracking. So if the goal is to do teleoperation, there are better ways to do it. If the goal is to do computer vision and something else, then obviously like something with the markers on the fingernails is not going to be published at like whatever a computer vision conference. But what's the goal here? Like, do you want to solve teleoperation or do you want to publish computer vision papers?
We did want to do something different for teleop. I know what systems you're talking about. Where I come from, we had 5 different motion capture systems, but they were still more expensive than this, certainly, and they don't capture like the thickness of your fingers and stuff like that as well, right? I mean, you get point measurements sort of on the peripheral of your hand, and you can still certainly work off that information, but we are trying to leverage models more. Yeah.
Look, I mean, the robot has rigid fingers, right? So if you map a finger on my fingernail to a point on my fingernail to a point on the robot's fingernail, you're done. Like, you don't care about the thickness of my finger, right? And as Sid was saying, humans are going to adapt almost. I mean, the reason I say that is because, I mean, I've been doing similar things 20-some years now, but most recently with OptiTrax that cost like $3,000, and it tracks at 120 hertz. The errors are way smaller than what you're doing, and you basically forget about the tracking, just focus on the data operation. And you're right that some of the fancier mocap systems cost a lot, but you can re-engineer the mocap system. So here's what I'm saying: put little reflective pieces of tape, shine infrared line on them, treat it as a computer vision problem, but now you have these perfect features that are just glued to your hand. They're never going to be mistaken. They'll never go away, and then do the rest. It's just the most sensible way to do it. And the only inconvenience is that you have to spend like 20 seconds gluing like tape to it.
So, I mean, there's certainly other viable solutions to this, right? But I don't think there's anything incorrect with trying it completely markerless, right? And then you just need a couple of cheap cameras, right? And the engine to run it. That's it. And we've actually had other users walk in on the fly to try the system. They don't need to paste things on them and anything like that. You can just walk up, stick your hand in, and go. Yeah.
Now, in the interest of time, maybe one.
I just want to say that like nowadays with everyone's phone having that camera, it's much easier for just everywhere you go, you can start controlling something virtual or a real robot. So I don't know. Let's say I go somewhere and put my phone and control some robot, for example.
But
without
the
having to do
Sam
any.
robot costs like $50,000. It's not like the world is full of Sam robots that people randomly walk in and control.
Well,
That is well.
I mean,
Anyway.
All right. Thanks.